My name is Jordan Christian, and I am a postdoc in the School of Meteorology at the University of Oklahoma. And in this presentation, I'll be covering flash droughts in global climate models, specifically across the central United States. This is actually an excerpt from a global study looking at flash droughts in climate models, but here just taking a more of a focused approach, looking specifically over the US. And before I get going, just want to acknowledge my co-authors, Eleanor Martin, Jeff Becerra, and Jason Furtado. So before I begin, first I want to talk about what actually is flash drought. Well, flash drought is defined and characterized by the rapid intensification towards drought. And this is a word definition, but helps to visually see what a flash drought looks like on the environment. So this image here is taken from a phenocam site in Miranda, Oklahoma, back in July of 2012. And the image on the right shows just 30 days later how rapidly the environment desiccated. And this visually shows how fast a flash drought can develop and how fast it can impact an environment. So this is what we're looking at when we talk about flash drought. In terms of the impacts, there's several. First of all, when you start to see that rapid intensification towards drought, you're going to see a rapid depletion of the near surface and root zone soil moisture. As flash droughts continue to develop, they're going to start to place excessive moisture stress on ecosystems. Ultimately, once you have a flash drought that fully develops, you're going to start to really see, impacts on agricultural areas. And lastly, once you have a flash drought, you start to see also an increased risk or the promotion of the ingredients necessary for wildfires and other features such as heat waves as well. In terms of this specific study, why we want to look at flash droughts in global climate models, global population is going to rise or expected to rise significantly over the next 3 decades. And associated with this increasing global population, there's going to be an increase in the demand for agriculture as well, with a projected increase of double just by 2050. And why this is important and associated with flash droughts is that flash drought is at the intersection of not just water resource and a depletion of water resources, but also food security as well. And the fact that flash droughts develop on relatively short timescales, on the order of 4 to 8 weeks, this is relatively, this is much faster compared to conventional drought development, which occurs over several months or seasonal timescales. So given all these impacts, flash droughts are very important to study, especially in the future of climate, to see what we can expect in terms of their frequency and other characteristics. So specifically for the presentation today, I'm going to be focusing on 2 different research questions and addressing 2 different research questions. The first one is, what types of trends or changes do we see in the flash drought frequency across the United States? And then secondly, how does the agricultural risk change from flash droughts in a future climate? And we'll be looking at that today with various scenarios. So just a brief overview of the methodology used for this analysis. First of all, we use the standardized evaporative stress ratio, Caesar, and soil moisture to identify flash droughts. Just as a quick summary, the evaporative stress ratio is defined as ET, or evapotranspiration, divided by PET, or potential evapotranspiration. And given this ratio, it provides an overall measure of the moisture stress on the environment. And what we do here for the study is we essentially take these ESR values and standardize them so that they're comparable across space and time. Just to show a quick schematic of what Caesar looks like and how it's defined or used to define flash drought. We have an image here showing Caesar in the red line, and the tan region is the outlined area of flash drought development. And generally, when you start to see decreasing values, rapidly decreasing Caesar values, are going to be approaching drier and warmer climates, or drier and warmer environments. And in contrast, if you see Caesar increasing, you will see be going towards wetter and cooler conditions overall. So in terms of how we identified flash drought specifically in this study, we used a framework from Christian et al. 2019, modified further in 2022, using 3 different criteria. And we'll go through this very briefly just to show how these work. On the left image here, down on the bottom, I have Caesar with the red, soil moisture on the right in the blue, and the tan region is highlighting the identified flash drought using the data and the criteria listed here. So the first criteria is making sure we just have a rapid change in Caesar or the evaporative stress at or below the 25th percentile. So that's indicated here on the left, showing that period of significant drying. And then also to verify the drought component, or making sure we are reaching drought conditions, we want to make sure that we have see soil moisture values below the 20th percentile. So that's what we see here on the right image, showing that the solid blue line soil moisture is crossing over the threshold of the dotted blue line, which is the 20th percentile. And then lastly, just making sure that we separate flash drought periods from dry spells. So making sure that the overall flash drought event is at least 30 days. In terms of the data sets used here, we used 4 different reanalysis data sets to essentially represent our observational period or our observations. And then we used several climate models. Here we used 6 different climate models, and ultimately these 6 were chosen as they provided the necessary variables needed for the analysis, and also provided the variables on daily timescales. And as we go through all the results, all these data sets are bilinearly interpolated to a 1 by 1 degree grid, ultimately to allow them to be averaged together in the results. Going through some of these scenarios here. So the first one to mention is the historical period. So the models provide a historical period from 1850 to 2014 to essentially simulate the period between the pre-industrial up to present. And then we have 3 different pathway or scenarios that we used in this study to explore how flash drought changes across these different scenarios. So these are SSP, socioeconomic pathways, combined with radiative forcings. And so the first pathway, or the first scenario, SSP 126, this is essentially a more conservative pathway with low radiative forcing by the end of the century, and the SSP 1 socioeconomic conditions, more geared towards sustainability. And then we have a middle of the road pathway, SSP 245, with medium radiative forcing. And then lastly, SSP 585, which is the high end scenario with a high radiative forcing and significant fossil fuel development, all towards the end, especially towards the end of the century. So I'll start going through some of the results. First thing is taking a look at historical flash droughts. Specifically, how do the models, what is the model skill when quantifying historical flash drought? And so this figure here shows the composite of all the models and their general flash drought occurrence or flash drought frequency across the United States. And so we see here that we have a hotspot for flash drought development right through the central US. This aligns with several other studies in the scientific literature showing that there is a hotspot across the central US. And so this is an initial first step, or gives initial confidence that the models are performing relatively well. But we can take it a step further. We can start to compare, first of all, spatially to see how the models did against observations. And so taking a look here, the yellow and oranges and red colors on the color bar indicate that the models are overestimating flash drought occurrence in the historical period, and blue colors indicate that the models are underestimating flash drought in the historical period. So just a couple of regions to note. First one in the Northwest, we see a slight overestimation of flash drought overall, but really it's only around 5%. In terms of the overestimation, pretty low. Once again, we also have another region right through the central US, that hotspot region, with a slight underestimation of flash drought, but once again, generally under 5 to 10%. And the bias on underestimating flash drought in the models. The biggest area, or the biggest bias we see in the models, is in the Southeast, showing an underestimation of flash droughts between 10 and 20%, specifically or especially in Florida and Georgia. But for the most part, most of the US is relatively, or the models relatively capture the frequency of flash drought compared to the observational period. And most importantly, specifically across the central US, which is a little bit more the focus of the study today, the biases are relatively minimal. Last thing I just want to point out here is there are dots indicating statistical significance in the difference between the models and the reanalysis data. But for the most part, you can only see that there are actually only a few dots, mostly in the Southeast. So for the most part, there's no location in the US really where there is a significant difference between the models and the observational data. So that was the spatial analysis. We can also just take a quick look at the temporal analysis to make sure that the seasonal cycle of flash drought is also captured. So looking at the period between 1980 and 2014, we can see that generally there is a higher flash drought frequency in the summer months. This is seen in the black line, kind of observational data sets. But for the most part, the historical models are able to capture this seasonal cycle as well, showing an increase in flash drought frequency as you move into the middle of the growing season, and it starts to decline as you move towards the end of the growing season. So all this, both the spatial and temporal analysis, give confidence going forward that the models are able to relatively strongly represent flash droughts, both in the historical period and also gives confidence moving forward, looking at the future projections as well. So now start to look at flash drought in these different climate scenarios. So I'm only going to show one spatial map here of one of the scenarios, and then I'll show all three scenarios for the time series. But here, just generally showing what to expect. This is comparing the end of the 21st century compared to that historical period. And ultimately, we see with these yellow and orange colors, this is indicating that there's generally an increase in flash drought occurrence, particularly across the western US. And this type of signal is also seen in also the SSP 126 and also the SSP 585. It's the least strongest signal in the 126, but also has the high signal in the 585. So this kind of gives a middle of the road result for what the climate models are projecting. Not necessarily anything that reaches statistical significance per se, but the models are showing somewhere between a 5 and 15% increase in flash drought occurrence, mostly over the western US. If we look at this in a time series, once again, now we're going to switch over a little bit towards the central US, because this is where the focus of the study is, where that hotspot of flash drought occurrence is. The models show an increase of flash drought frequency, specifically in that period, 2015 to 2100. All the models show an increase, but the largest increase seen at the end of the 21st century is shown by the SSP 585 scenario. And now taking a look at the agricultural risk from flash drought under different future pathways and scenarios. First, take a look at the cropland area. So this is actually going to be all over all of North America, not just the central US or not just the United States, but all of North America. And for the most part, over the continent, the cropland area has increased significantly during the historical period. And cropland has also been affected by flash drought during this time period, and it has increased, but this is also partly due to the increasing land use for agriculture. As we look at the historical period, we can actually see that the total cropland is projected to remain relatively stationary throughout the 21st century, and this is regardless of the pathway. Some pathways, like the 245, show the most agricultural land use, with other ones like the SSP 585 actually showing the least by the end of the 21st century. But what this is showing here is the total land area. So what we can do is also look at the total percentage of croplands that are experiencing flash drought to see what kind of impact flash drought is having specifically over agricultural land area. And in the historical period, we actually see that flash drought occurrence has remained relatively stationary. But when we look at the future period, we actually see an increase in the risk of flash drought. So in SSP 126 and SSP 245 scenarios, we see a moderate increase in flash drought frequency, but we see the highest increase in the SSP 585 scenario indicated by the red line on the graph. So just some conclusions from the study. First of all, flash drought frequency was expected to increase, or is expected to increase between 5 to 15%, with a specific focus over the western half of the US. That was given by the medium scenario, but all of these increases were seen in all three scenarios. Particularly the SSP 585 shows the largest increase in flash drought frequency. And when we look specifically just at the US, we saw a 20% increase in the flash drought occurrence compared to a 9% and 11% in the SSP 126 and 245 respectively by the end of the 21st century. And then lastly, the agricultural risk is also expected to significantly increase. This is seen once again in all three scenarios, but varies by the degree of each scenario pathway. So in SSP 126, 245, we see a 9 and 15% increase respectively across agricultural areas, but in the SSP 585 or the high end scenario, we see a 45% increase in flash drought over agricultural areas. And that's all I have for this presentation. If you would like to follow up with me with the research presented here, my contact information is below. Thank you.